Hello and welcome to another video. In this video we move on to section 3.3, Trigonometric Substitution. This is everyone's favorite section. If you can't tell, I'm being sarcastic. These problems involve plugging in trig identities, using what we learned in section 3.2, also using SOHCAHTOA, and lots of algebraic manipulation. So they're pretty long, but lo and behold, they allow us to evaluate integrals with integrands of the form square root of a squared minus x squared and square root of a squared plus x squared. And we've seen some integrals that look a little bit like this, but not all. So this will allow us to evaluate even more kinds of integrals. And we'll have one distinct strategy for the a squared minus x squared and another distinct strategy for the a squared plus x squared. So the problem solving strategy for the minus sign, problem solving strategy for square root of a squared minus x squared. So the first thing you always want to do is make sure that you can't use another technique. So you want to go through our toolbox, and remember we have U substitution, we have integration by parts, right? And we also have the stuff we learned in 3.2 with the trigonometric integrals, with the trig identities. So you want to make sure that the integral cannot be evaluated easily another way. And again, why? Because like I said, this method is pretty long and involved. So if you can avoid it, you want to avoid it. Right, so for example, the integral of x over root a squared minus x squared dx, right? You can use U substitution on there because you know the derivative of this, right? Because a squared is just a number, right? I should make that clear. A squared is a constant, right? So when we take the derivative of a squared minus x squared, we'll just get minus 2x, which we can change to cover, right, these x's on the outside with the dx. So U sub would work on these, right? So if you can use U sub, you want to use U sub or integration by parts or anything like that. If not, what you're going to do is let x equals a sine theta, right? Where this a here is from the square root of a squared minus x squared. Right, so a is just equal to the square root of a squared, and then dx, right, the derivative of sine is cosine. So the one way that you can remember this is when you have a minus sign, that minus sign there stands for sine, right? So that's the trick. Minus sine equals use sine for the substitution, and you'll see why I point that out when I go over the plus sign, right? Because for this plus sign, we're going to use tan. So the plus sign stands for the t in tan. Okay. So once you do your substitution, the next part is to simplify as much as possible. And then the fourth step after you simplify is to evaluate, right? Because now we're changing it to be an integral with trig functions. So you're going to evaluate the integral using the methods from section 3.2, right, the trig integral section, which is why we have to go through that section before we taught this section. And then 5, you need to rewrite just like U substitution, right? This is another type of substitution. Here we're substituting using trig functions, right? So that's why it's called trig substitution, right? But remember, we don't want to have an answer in terms of theta, we want to answer in terms of x. So we need to rewrite the results in terms of x. So let's do an example. So let's say we were told to evaluate the integral from root 9 minus x squared dx, right? So, right, this is of the form square root of a squared minus x squared. So here our a squared is 9, so that makes our a 3, right? And right, notice we have a minus sign, so that tells us to substitute x equals a sine theta, which, right, in this case we said a is 3, so that's 3 sine theta, and then dx is just 3 cosine theta d theta, right, the derivative of x. And so then, right, if we look at our steps, what did we do? right? This integral can't be evaluated using u sub or integration by parts, right? Because this isn't a product of two functions, and also this isn't one of the regular antiderivative formulas, and also this isn't a chain rule where we don't see the derivative of the inside part somewhere multiplied on the outside. So we know we can't use u sub for it either. And so our only resort is to use trig substitution. So we did number 1, right? And we did number 2. And now we need to plug those things in and simplify. So the integral that we're starting with is root 9 minus x squared dx, right? So I'm going to take my x and plug it in here. So this is going to become the integral of the square root of 9 minus 3 sine theta all squared. And then dx, right? dx we said was 3 cosine theta, so I'm going to plug that in outside of the square root. So that's 3 cosine theta d theta. And now I want to simplify. Well, notice what is 3 sine theta squared, right? That's 3 sine theta times 3 sine theta. So we know 3 times 3 is 9, and then sine times sine, that's going to be sine squared theta. So this is going to become the integral of the square root of 9 minus 9 sine squared theta times 3 cosine theta d theta. I'm going to just erase my scratch work. Okay, so now, right, if we notice, there's a 9 in common that we can factor out of inside of the square root because it's on both of the terms there. And I think this is as simplified as this is going to get, right? So remember, we want to use trig identities as well. So we know that sine squared theta plus cosine squared theta is 1. So we know that 1 minus sine squared theta is cosine squared theta. So I'm going to replace this 1 minus sine squared theta, right, with cosine squared theta. So this is going to become the square root of 9 cosine squared theta times 3 cosine theta d theta. Okay, we're making progress. So notice, right, 9 cosine squared theta, that's the same thing as 3 cosine theta times 3 cosine theta, which is 3 cosine theta all squared. So we could actually take the square root of 9 cosine squared theta, right? That's just going to be one of the 3 cosine thetas. Remember, the square root cancels out the square, right? This square here cancels out this one here. Okay, so then we're left with this, and we can simplify that as well, right? This is 3 cosine squared theta d theta. And notice, we're still at a integral with a trig power, right? We could simplify this by pulling out the 3. Remember, if we only have an even power from section 3.2, you want to replace, right, this cosine squared theta with the even power trig identity, which was 1/2 plus 1/2 cosine 2 theta, right? So this is going to become 3 times the integral of 1/2 plus 1/2 cosine 2 theta d theta. Okay. Oops, I totally forgot to, right, I dropped one of my 3's here. I forgot to do the 3 times the 3. So really this should have been a 9. You guys are probably so sick of me by now, but I'm sorry, I promise I'm just human. And I'm going to show you the real and the raw. I'm not going to edit it out and redo it, you know, because we all make mistakes and we got to catch ourselves when we do and learn from it. Okay, so now these things are integrable, right? Because what you have to notice is what we can do is we could split this up into 2 integrals pretty much like this. 9 times 1/2 d theta plus 1/2 cosine 2 theta d theta. And so we can do a u substitution on this integral here, right, where we let u be 2 theta and then we let du be 2 d theta, right? So 1/2 du is d theta. So this integral becomes 1/2 cosine of u times 1/2 du, right? This replaced the d theta in here. So this becomes, we can pull out, right, 1/2 times 1/2 is 1/4 times cosine u du. And what's the antiderivative of cosine? That's sine. So this is just 1/4 sine u, right? We have our plus c, and the u we said was 2 theta. Okay, so, and then the integral of 1/2 d theta, right? Since we're integrating with respect to theta, we know that it's just going to add a theta there, right? Because the derivative of that would be just a half. So we could bring this all down, and we have 9 times 1/2 theta plus 1/4 sine 2 theta plus c. And so then we can distribute the 9 and get 9/2 theta plus 9/4 sine 2 theta plus c. It may seem like, oh, we're done, but remember, we're given an integral in terms of x, right? That's what they were asking us for. Whoops, an integral in terms of x. And so we can't give an answer in terms of theta, but that wouldn't be sufficient, right? So that's why the last step is to rewrite the results in terms of x. So how are we going to do that? The key thing is to use this relationship here that we started, how we changed from theta to x in the first place, right? Which was doing the substitution with x equals sine of theta. So how are we going to do this? Well, right, what we can do is, let me just rewrite this. So we have x is 3 sine theta, right? So then we know x over 3 is sine theta, right? And what we can do is we can take the arc sine, right, the inverse sine of both sides, right? So if we do that, remember, inverses and regular functions cancel each other out, so what we're left on the right with is just theta. So theta we know is inverse sine of x over 3, right? So that'll help us. We can plug that into here, but we still don't know what to do with this sine to theta. Well, you're gonna have to recall another trig identity from pre-calculus that says that sine 2 theta is equals to 2 sine theta cosine theta. And we know that sine theta, right, we said sine theta is equal to x over 3, but what is cosine theta then? Well, that's where SOHCAHTOA is going to come in handy. So just as a refresher, remember, SOHCAHTOA means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. And so we make a right triangle. And remember that the side directly, right, the side across from the right angle is the hypotenuse, and then I have to decide one angle to make theta, and the side across from theta is considered opposite, and the side right next to theta is considered adjacent, right? So we have that x over 3 is sine theta, but also we know from SOHCAHTOA that sine theta is equals to opposite over hypotenuse. So now we know our opposite side is equal to x, and our hypotenuse is equals to 3. And so we can solve, right, using the Pythagorean theorem or anything else that you can use to find the adjacent side, right? So remember the Pythagorean theorem says a squared plus b squared is c squared, right? Remember c squared is the hypotenuse. So let's just make x a, and we're trying to find the adjacent side, which will be whatever b is, and then our hypotenuse is 3. So this becomes x squared plus b squared is 9. And so then what we can do is we want to solve for b, so let's subtract the x squared from both sides, so we're left with b squared on the left, then we have 9 minus x squared on the right, and then we take the square root of that, and that ends up with 9 minus x squared. And one hack is that the third side of the triangle, if you set it up correctly, should always come out as the part of the square root of your integrand. So this side is the square root of 9 minus x squared. So now we know cosine theta, right? So what tells us is the adjacent side over the hypotenuse. So we just figured out what the adjacent side is. That's 9 minus x squared, and the hypotenuse is 3. Okay, so now we could plug all of this into our answer. So the answer that we had was 9/2 theta plus 9/4 sine 2 theta plus c. And theta we said, right, theta we said was just arc sine of x over 3. So this becomes 9/2 sine inverse of x over 3 plus 9/4, and we said sine 2 theta is equals to 2 sine theta cosine theta plus c. So then, right, we can first simplify the coefficient. So that's going to become 18 over 4. And then sine theta we said was x over 3. And then cosine theta we said was the square root of 9 minus x squared all over 3. Then we have our plus c. Right, so then this becomes 9/2 sine inverse of x over 3 plus 18 over 12 x times the root 9 minus x squared over 3 plus c. So we could combine that all to one term. Right, so notice 18 divided by 12, we could divide both of those by 6, right? So this will become 3 over 4. So, and then we can actually cancel out, right, this 3 with this 3 since we're multiplying those two things. So this becomes 9/2 sine inverse of x over 3 plus x times the square root of 9 minus x squared all over 4. Remember, for fractions, you just multiply straight across. Oh, and this shouldn't even be a 4, right? Because 12 divided by 6 is 2. So this should really be a 2. Okay, and that is the very first problem. So as you can see, these are probably the most involved problems we've done so far this semester. But once you get the hang of it, it's not as bad, right? You just have to get familiar with this process, right? Once you determine you need trig integrals, you do your substitution based on if it's a minus sign or a plus sign, you simplify, you use trig identities, you integrate in terms of theta, and then you have to rewrite your results in terms of x, and you're always going to do that using whatever you used, whatever you used to substitute and setting up a triangle and using SOHCAHTOA. Okay, so before we end this video, I just want to talk about when you have a plus sign in the middle. So the problem solving strategy is pretty much analogous. The only thing that changes is what you substitute in. So problem solving strategy for integrands of the form a squared plus x squared. So remember, the key thing that I mentioned earlier is that when you have a plus sign, the trick to remember is that when you have a plus sign, the plus sign symbol you could think of as the t in tan. So what you're going to plug in is going to be with tan. So, right, the first step is the same as that last one. First, check that the integral can't be evaluated another way, right? Because we want to avoid this if we can. And then if not, you're going to move on to step 2, and you're going to let x equal a tan theta, right? And that makes, remember that the derivative of tan is secant squared, right? And so then you're going to end up using the trig identity just so that you know 1 plus tan squared theta is secant squared theta. And then you're going to simplify, and then you're going to evaluate the integral. And again, like last time, you're going to rewrite it in terms of x using the triangle and SOHCAHTOA to rewrite the result in terms of x. And in the next video, I'll do an example of that.